Wonderful. Thanks a lot. It's great to follow up such an awesome talk. Today, I'm going to be talking about recent work that I've done with my collaborators on quantum machine learning. And the basic idea that, can you guys hear me? I'm hearing a lot of noise in the background.
Yeah, you're echoing a little bit, but
Okay, fantastic. So the basic idea that we're proposing here is we're proposing looking at a very particular type of quantum learning. In particular, we're looking at generative learning, where we're aiming to not just be able to discriminate between quantum states, but we'd like to be able to build a model that can actually replicate these. And the key thing is with these results is that we find that we can actually train quantum models for generative tasks using these objective functions efficiently in many cases, and also avoid all known Barren Plateau results, which is something that's actually pretty cool because, well, yeah, it's a major problem. But before I begin jumping into more details about this, I really kind of just want to talk a little bit about like kindergarten level stuff before we can kind of get into, the rest of it. So we've all seen machine learning at this point, but just for those of you who haven't looked at it in too much detail, really what we kind of want to do is we really want to be able to, machine learning is a set of techniques that we end up using to be able to build models for data that we experience in nature. So for example, if we wanted to build a cat detector, the way that these models are built is rather than coming up with a deterministic way to say, what is a cat or what isn't a cat, for example, we would feed in a bunch of images, in this case of something that's very clearly a cat and very clearly not a cat. Um, we feed those images into the model, and then we would train it with respect to an objective function. And this training basically ends up boiling down to a gradient descent process. You've got some figure of merit, which might be how accurate, for example, it gets the right label assigned with the right class of image. And then what we want to do is tweak the parameters of the model in order to maximize that probability. So this is one of the reasons why I feel kind of grateful to be talking right after Tong Yang, because his ideas kind of flow very naturally into the sorts of problems that I'm going to be talking about here. And so one of the big areas or big successes that we've had in machine learning is this idea of deep learning. And the idea of deep learning really is that what we want to do is we want to try to build a hierarchical model of the data that we're generating. So for example, if we wanted to build a cat classifier, like we were talking about before, the idea behind these types of models is that what you would do is you would begin by feeding a raw image in on this side. And this is stored in these neurons over here. And neurons for our case, we can just envision as being individual bits. So like each pixel in a black and white image, we could envision being represented as a bit, saying whether that pixel's on or off. All of those are fed in. And the network, rather than making a decision about whether it's a cat or not based on the raw pixels, what it does is it starts generating higher level features at different layers of abstraction. And these neurons that we're using in this region, these are often called hidden layers or hidden units. Okay. The reason why is because at the end of the day, to figure out the output class that we're providing for the image, we actually only care about these two neurons at the very end. All the rest of this stuff in between, which generates high-level features, they're just used in order to make this ultimate decision that we have in the end and are fundamentally discarded. So the basic idea is that what we do is, oh, I should just erase this text. I forgot about the animation. So basically what we do in this process is we train it with gradient descent, but we also ignore all of this stuff in between. Okay. And this is something that actually is very important for reasons I'll get to in a moment. But one of the things that okay, I guess I skipped a step here. If we want to talk about quantum computers and doing quantum versions of this, rather than having, a cat image being put on this side, what we would have is we'd have something kind of like a cat state now being put on the inside. Then what we would have is we would have a whole bunch of extra qubits that we use in order to be able to generalize or find, train an effective optimal measurement in order to be able to classify the quantum states that are coming in over here. So the way that we can picture this is that what we do is we have a bunch of, we've got a quantum state that's of the form psi visible coming in. And we've got an additional register off to the side, which is a hidden subsystem. And a hidden subsystem is all this extra memory that we're using in our particular model. Then what we have is the standard approach that we would use for this is we would want to build a unitary model on this that ends up mapping these quantum states in such a way so that the trace over the hidden of the unitary of theta acting on the initial state, psi v, tensor psi h over here, ends up giving us a final state that we can measure and glean some useful information from. So this is the kind of the standard model for quantum machine learning that we typically use these days. Now, lately, this model has been somewhat upended because of insights that actually these types of models can actually, in many cases, be next to useless. And in fact, in some cases, having quantum effects in these systems can actually make the models weaker than classical models. So the first of these realizations was given by Jared McLean and company. And the basic realization was that if we consider our quantum models as being like a unitary that we're applying to the quantum system, if we choose these unitaries arbitrarily, and let's imagine that each of the unitaries was chosen by arbitrarily, I mean, uniformly according to the Haar measure. Technically, actually, for the T-design nerds in the crowd, we only need a two-design condition. But we imagine it's chosen according to the Haar measure. What we can then show, actually, is that the variance of the derivative of our objective functions in this case actually ends up being strongly concentrated near zero. And so what that ends up meaning is that with extremely high probability, if we take a random model and just choose our parameters arbitrarily, and that the resulting unitary is typical of a Haar random unitary, then the variance that we end up getting for our gradient is next to zero. So that means basically we run into these situations like what Tong Yang was just talking about. Everywhere basically becomes a saddle point. And the gradient isn't just small, it's actually exponentially small for all but an exponentially small fraction of the configurations that we could consider. And so this is a really, really scary result. And it says that if we want to take advantage of quantum machine learning in these cases, we really we can't begin with a naive model. We have to have a atypical unitary that we're putting in, something that's very different from these Haar random unitaries. The next result that ended up coming up that my co-authors and I showed that was also very scary is that you can run into a problem that we call entanglement-induced Barren plateaus. And this is an example here of what people would call in the community a quantum neural network. So each of these Gs you can view as a parameterizable gate. And this would be a sequence of parameterizable gates. And imagine what we've got is we've got 4 visible qubits in this and 4 hidden qubits in it. So what we would do in this particular case is that we would like to train a training objective function. And by measuring the expectation value of this qubit at the top, that's basically going to be our objective function. We'd like to get this measurement result to be 1 in all of the 1 cases and 0 in all of the 0 classification problem. So if we end up having a complicated network of parameterizable gates, then what will end up happening is that these subsystems will end up becoming nearly maximally entangled. Then if you end up having a maximally entangled state like 0, 0 plus 1, 1, right? And you decide that you want to do a partial trace over one of those 2 qubits, you of course end up with a maximally mixed state. on the other subspace. The exact same thing ends up happening with quantum neural networks. If we have a ton of entanglement that's generated between this hidden subsystem and the visible subsystem that we're outputting in the end, then actually the resulting quantum state ends up becoming nearly maximally mixed. And in that case, you can actually end up showing that not only is the objective function measurement that you get in the end no better than what you would get from just sampling from the maximally mixed state with high probability if you have this degree of entanglement, but also the derivatives that you end up getting for these types of models are also going to be with high probability exponentially small, meaning that you cannot escape from these situations. So what this ends up saying is that if we want to build analogs of quantum deep networks, we have to worry about the entanglement between these two and make sure that we're using entanglement in ways that are profitable for our model and not in ways that are directly harmful like this. Now, this is somewhat of a new insight for the quantum machine learning community, but interestingly enough, this is a very, very old insight for the thermalization community. For people who take a look at the foundations of thermodynamics for closed quantum systems, this is exactly the same mechanism that explains how the sort of canonical canonical as well as microcanonical probability distributions end up emerging for closed quantum systems. So all of this fact that entanglement between a system like these visible units and the bath down here is ends up leading to something that looks like thermalization is an old idea, but it's newly being applied to quantum machine learning. And it really suggests that there actually, are some deep connections between these two fields that are just beginning to be explored. So this is a major problem. And so we've got to make sure that we don't run into these barren plateaus when we're training a network like this from just the Hilbert space dimension being large, like McLean et al. Talked about to begin with. But we also, if we have these hidden subsystems, we have to make sure we don't get this pernicious entanglement building up between the part of the state we care about and the part of the state that we're just using as a scratch pad memory to design our models. And so these two constraints make it actually very difficult for us in practice to be able to say with confidence that we can train models. So the question is, well, how do we do it? In part, the solution that my co-authors and I are proposing is to actually take a look at a slightly different problem. Instead, what we'd like to do is, rather than discrimination, we'd like to take a look at the problem of generation. And so the idea of generation is actually very similar to building an approximate cloner. Imagine you've got a box, right? And with this box, what we'd like to do is this box is a unitary circuit, and it's parameterized by some parameters theta. What we'd like to be able to do is give it a feed in an algorithm, a number of copies of particular states that we'd like it to generate. And then we'd like to learn the parameters that will end up leading to the box outputting states that minimize the distance between the output quantum state and the input states that it was trained with. So that's the whole idea behind generative training. And the simplest version is really just like an approximate cloner. The next simplest version, which I'm not going to spend too much time talking about, would be one that conditionally generates the state. And this is something more like what you would see with autoencoders or other models that basically attempt to try to create an identity map between the inputs and the outputs. But nonetheless, this former problem can be seen as a subroutine for the later problem. And I should mention there's a number of different approaches in classical machine learning end up taking this. For example, Boltzmann machines were an early, very popular approach for dealing with this, for doing generative learning. And autoencoders also are used much more frequently these days for generative tasks. But there's been a lot more popularity that's come about because of generative adversarial networks, which, although they're a little bit different than a purely generative model, they strongly end up employing generative models as a subroutine inside of the game that they end up playing between a prover and a verifier in order to classify data. But to give you an example of this, this is a data set that I've shown for far too many years that came out from some early Boltzmann machine work from Solokutinov and Hinton. And the basic idea behind this is that what they did is they trained a neural network with a bunch of images on the left. And then once the neural network was trained, then it was capable of generating particular examples of images that look eerily close to the original images that it's trained with. And our task here is we'd like to be able to do the exact same thing, not for images, but for quantum states. So before we begin, whenever you're approaching any problem in quantum machine learning, I really think that, the right thing to ask yourself is, what's the right distance measure that you want to take a look at? Now, many early works had taken a look at the inner product between the input density, or the input states, and the output states as their figure of merit for how well the network is working. And it's a nice metric in the sense that it's easy to compute using the swap test. However, it suffers from all the known Barren Plateau results that I mentioned earlier. So that means that unless you've got some intuition before you start, the gradients that you end up getting for trying to optimize this objective function can be exponentially small. However, there's other more information theoretic based metrics that can be used. And the one that I personally like the best for talking about how similar two quantum states are is, of course, the quantum relative entropy. And the quantum relative entropy, basically what it does is it measures the number of bits that you need to encode one quantum state using the other with the optimal encoder. And it can also be used in order to be able to bound the number of samples that you need to optimally distinguish between two quantum states. It's very nice because it's got a good motivation, but there's two important reasons why, or actually probably one really important reason why it isn't used all that frequently. It's because of the fact that this object contains matrix logarithms. And if we want to train this, then we're going to have to differentiate matrix logarithms. And that's a major pain. So okay, well, why is this such a pain? Well, just to give you an idea, you might think, oh, well, if we take a look at the derivative of the relative entropy, assuming that sigma is a parameterized quantum state and rho is just a constant, then the only term that's non-constant in the previous expression I gave is the cross entropy, the trace of the density operator against the logarithm of the parameterized one. And you might be tempted to think, hey, well, I know how to differentiate logs, right? The derivative of the log is just, well, derivative of sigma divided by sigma. But unfortunately, that rule only ends up working if the chain rule works. And one of the assumptions made in a derivation of the chain rule is that the derivative ends up commuting with the function. And that doesn't occur here. In fact, the cleanest expression that I know of for the derivative of a matrix logarithm is this integral expression. And so if we wanted to implement this on a quantum computer, we'd have to build this guy over here. And we can do that at great cost using a linear combination of unitaries ideas, but it's a real serious pain to do this on a near-term quantum computer. So the question is, can we do something kind of a little bit easier? And the thing that we settled on was looking instead at instead of this at the maximal Rényi divergence. And the maximal Rényi divergence basically is it kind of generalizes and upper bounds the quantum relative entropy. And one of the nice things about it is it's positive. It's zero if and only if the two states that you're considering are the same. And on top of that, it upper bounds the regular Rényi divergences, which for alpha greater than 1 are upper bounds on the quantum relative entropy. So by training this objective function for any alpha greater than 1, what you can do is you can also guarantee that minimizing it to 0 will also minimize the quantum relative entropy to 0. So that is fantastic. The other thing that's really cool about this is that for the alpha equals 2 case, it has a very simple expression. It's just the logarithm of the trace of rho squared sigma inverse. And note that in this case over here, it's the logarithm of a scalar, not a matrix now. So because this is an ordinary matrix logarithm, not a matrix logarithm, we can now differentiate this objective function. So the one thing that I wanted to mention, it's a little bit of an annoying point, is that unfortunately the order that you end up taking the two terms for Rényi divergences as well as quantum relative entropy slightly changes the result. So we have to decide on one of two possible choices. Do we take our parameterized model that's generating the states to be the first argument, or do we take it to be the second argument? It turns out that in practice, the second one is much more convenient, where we end up taking the parameterized state to be the first argument. The reason why is that the derivative ends up forming having a very simple form in this particular case. So that's basically what we end up doing. So the basic idea that I wanted to mention here is that in order to make some more progress and be a little bit more concrete about this, we need to come up with a functional form for what sigma is in order to be able to explicitly write down what the derivatives of our model are. And so we're going to take the convention that is used almost ubiquitously throughout, the QAOA community, quantum optimization, as well as quantum chemistry, and end up assuming that our initial state that we have is just going to be a product of matrix exponentials multiplied by some initial fiducial state that we'll choose arbitrarily to be zero. All the HJs that we choose in this model need to be efficiently simulatable. So in particular, choosing them to be one sparse is an appropriate choice, but in most cases, people choose them even more particularly to be poly operators. Then the other thing that I wanted to mention is that, there's going to be, in principle, both hidden and visible qubits in this model. And what we want is we want our resultant model for the state to be the partial trace over all of these hidden units at the top, which we're just using to generate correlations, or actually impurity in the resultant state. So one of the things that I wanted to mention is, okay, well, what about entanglement-induced Barren plateaus? Does our result immediately fall apart for the exact same reasons I mentioned before? Well, technically not, actually, or at least it doesn't trivially follow. The reason why is that result was talking about the concentration of an expectation value of a objective function like O objective, where that's just some matrix, traced against rho. But here we've got our objective function, in effect, being a nonlinear function of theta. So that means that basically, because the previous case ended up assuming that we have it being linear, and now we've got a nonlinear case, a lot of the stuff that we used before doesn't work whatsoever. And in fact, we're not able to just directly turn the crank and show that this ends up leading to exponentially small gradients. So that's one of the things that's really kind of neat. We can end up going through this expression for sigma, and one of the things that's very nice about it is that once we've chosen sigma to be a product of operator exponentials against this fiducial state, then we can just end up using the product rule now to differentiate each of these individual operator exponentials. And going through, we end up getting the following result, which we can then simplify down to this expression for the gradient, which essentially ends up boiling down to an anti-commutator of partial traces of the commutator of the Hamiltonian that we're interested in, time evolved, with a commutator with sigma. So that's the expression for the gradient. And now everything else that I'm going to be talking about in the next little while is just arguing how we can evaluate the gradient expression. Okay. So the first thing that I wanted to mention is, okay, well, what about this rho inverse, right? Rho here in our context is the training data, the state that we'd like to mimic. So even if we're given the state rho in some sense, how do we end up finding row inverse? Well, we can actually always do that thanks to some work that's been developed over the years from the linear combinations of unitaries community that shows a polynomial approximation is possible to the inverse function for this. That depends on, in this case, the condition number of the density operator. So provided that the density operator is well conditioned, then we can end up using these techniques in order to be able to closely approximate the density matrix. But of course, if it's ill conditioned, then this doesn't directly apply. Then the next thing that I want to mention is that once we figured out a way of doing row inverse, such as using this particular trick, we need to worry about computing expectation values of traces of these Hamiltonians multiplied by unitaries multiplied by other density matrices. So how do we compute these traces that we have present? Well, the way that we do this is by using this circuit that we call the Swapamard test. The reason why we end up calling that is because what we want to do with it is we want to be able to do something that's kind of like the swap test and kind of like the Hadamard test. We'd like to be able to compute the trace of products of unitaries as well as density operators. And this particular circuit, which is literally a hybrid of the swap test and the Hadamard test, actually ends up doing precisely that. So we can run this circuit and use that in order to compute those products of expectation values of density operators and unitaries. When we go through and do this using linear combination of unitaries techniques, we can end up seeing that the number of queries that we need to an oracle that provides each of the exponentials of the density, or not the density operators, of the Hamiltonian terms, and also a block encoding of the inverse of rho. We specified it in terms of the block encoding of the inverse of rho because we didn't want to have to go through all the details of specifically the method used in order to generate the inverse. Because in some cases, it's a lot easier than in others. But under that assumption, the total number of gates and queries that we end up needing to these oracles in order to be able to compute the gradient ends up scaling like this. So this ends up saying at least it's a query efficient under these particular assumptions. And under the assumption that the condition number of rho is polynomial, we can also white box the block encoding of rho inverse. So that's fantastic. We can efficiently compute the gradients under some circumstances of this objective function. The next point that's actually very interesting is that once we have the objective function, we can go through this exact same Haar expectation values that we went through with the standard objective function. And the interesting thing, of course, is that because the objective function, right, has this bit in the denominator that's absent from the traditional expressions, what ends up happening is that the lower bound that we end up getting on the gradients from this, actually it ends up getting normalized by the fourth power of the density norm of the density matrix. And so what this means is that if this density matrix that's generated by our model is nearly maximally mixed, then actually the lower bound on the gradients that we end up getting from the Haar expectation ends up actually not necessarily yielding something that's exponentially small. So these generative functions, unlike the standard functions, which are just the expectation value of a matrix, are not necessarily exponentially small. And so we can, in certain circumstances, escape from these Barren Plateau problems by generatively training. So this is something that I think is very neat about this about looking at generative approaches. But as a particular example, let's talk about learning thermal states. So thermal states are a nice example for us to talk about. The reason why is that if you recall, our objective function or gradient over here ended up having a rho inverse coming in. And so, ordinarily we would need a complicated method for computing what the inverse of a density operator is. But let's consider the case of learning a thermal state. If we know what the Hamiltonian is, but we don't necessarily know what the thermal state is, well, then we can always express the inverse of the thermal state as e to the h times trace of e to the minus h. And so by plugging that into our expression for the gradients, we actually find this relatively nice expression for the gradient of the maximal Rényi divergence between a thermal state and the state generated by our model. And so we can run through this and either use importance sampling on a near-term computer, a quantum computer, in order to be able to assess this. Or for more long-term applications, we can use linear combinations of unitaries to get the best asymptotics. But in any case, if we run through all of this and end up looking at the asymptotics of, we end up finding that the number of queries that we end up needing to a prepare and select oracle for the Hamiltonian, as well as the unitaries used to describe sigma, we end up finding that the number of queries needed in order to compute the derivative of the Rényi divergence is this quantity. And it's important to note that if we're looking at a high temperature state, is in a state where this one norm over here is a small quantity, then actually this can be computed efficiently. Of course, we don't expect in general that this could be computed efficiently, because the ability to be able to prepare and sample from a low temperature thermal state would allow you to solve NP hard problems. And so if we could train a model like this efficiently, then in those cases, we'd be able to show that NP is contained in BQP, which nobody really in their right mind believes. So that's why, although it's only restricted to the high temperature case, this restriction is reasonable. So to give a bit of an idea, now that we've got this, the question is, how well does this work in practice? And from my perspective, actually, this works far better than any model that I've played with in the past. So previously, all the work that I had looked at really had kind of mixed results for increasing the number of hidden units that we were using in order to try to describe a quantum state. Here, what we ended up finding for a case of trying to learn a quantum circuit, a unitary circuit, for generating purely random 3-qubit density or 3-qubit thermal states, we ended up finding that basically as a function of the number of training epochs that we ended up doing, that the loss function actually was shrinking exponentially if we gave it enough hidden units. And the loss function, specifically the Rényi divergence, ended up becoming actually exponentially small in these cases. And so what that ended up meaning is that basically we had nearly perfect models that we were able to learn for these density matrices using just ordinary unitary circuits. And furthermore, the fidelities we similarly increased. And it's important to look at the fidelities as well as this metric, because of the fact that we're kind of like training for this test metric, this test loss function on the left. And the fidelity isn't something that we're trying to train for, but you see also that as we ended up increasing a number of hidden units, rather than hitting an entanglement-induced Barren Plateau like you might have expected, our model becomes nearly perfect. And so this actually ends up showing kind of the power that these models can end up having for learning generatively learning particular quantum states. So to conclude, we've given a new method for that can efficiently train quantum models, at least under some circumstances, using Rényi divergences. And this has some very nice results, because all known Barren Plateau results don't apply. And this lower bound that we ended up giving on the expected gradient squared ends up giving a result that is not necessarily exponentially small. And that's in contrast to ordinary approaches to training, which normally lead to unconditionally exponentially small results. And furthermore, all the numerical results that we've done show that this technique learns extremely well. And it ends up saying that, for applications in quantum machine learning and as well as simulation that require density operators, this approach can actually be a nice way of compiling more efficient methods for generating approximate Gibbs states than existing approaches might provide. But there's more work that kind of, yeah, needs to be done as a result of this. The first is, well, I mentioned that, this is a generative approach, and it doesn't have the drawbacks necessarily that a straightforward discriminative training would have, i.e. it doesn't run into the Barren Plateau results, at least in a trivial way. One of the applications that potentially ends up coming up is pre-training then these results. So the idea behind generative pre-training would be what you would do is you'd start with a training set, and then you would just train your model in order to be able to approximate that training set to begin with. That'll put you in the vicinity of a highly atypical region in kind of of Hilbert space, sort of. And then because you're not in a typical region, the typicality arguments that we end up needing for the Barren Plateau result don't apply. And so this could be a way in order to be able to escape from the initial bad gradients that you have at the beginning of many quantum machine learning algorithms. The other aspect is that having new and improved approaches to doing generative training can actually be used in generative adversarial networks, and particularly in quantum approaches to this. So an interesting idea would be to see how well this actually ends up coupling with those ideas and potentially coming up with new models for classification that are vastly superior to anything that we have at the moment. Thank you very much.
So Nathan, thank you very much for the talk. We have one question already from Bill. He asks, how does this approach work when rho is a pure state? Does replacing rho inverse with the pseudo-inverse work, or does everything break down because of condition number?
So, okay. Yeah, that's an extremely good point. So if you're training with a pure state, then things break down immediately. Under some circumstances, switching to the pseudo-inverse, as you suggested, is exactly what you want to do. In other cases, what you want to do is you want to say, okay, well, maybe actually I'm willing to not generate a perfect model of the initial state. If you introduce a small amount of noise to begin with, then you'll have potentially worse condition numbers coming in, but at least everything will be well defined. And so those are the two approaches. Either you inject artificial noise into it, or you use a pseudo-inverse.
Other questions? So I guess one question I have is with these models, right? So in the beginning, you said this is approximately cloning. How well does this help to learn the basis in which a quantum state is? I guess in the pure state case, it's very perhaps state in the unknown basis to simplify the problem.
I'm sorry, I couldn't quite hear you, James.
I said in the beginning, you said this is approximately cloning. I was wondering how does this help just learning the basis of a quantum state?
Okay, so basically, I guess the first thing that I want to be very clear about is that all that we're discussing in this paper is just the complexity of the gradient calculation step. We actually make no promises about how good of a model following the gradients will actually end up leading to. So in principle, it could be used in order to shed some information on the basic or the kind of like meaning of a state. But a lot of this ends up depending on the quality of the results that the gradient takes you to, which also kind of leads into Tong Yang's results.
Excellent. Any other questions? If not, we're right on time. I think there are more questions. Would this approach work with generative models using subspaces?
So generative models. I'm not sure what that means.
I didn't write it. It's anonymous, so I don't know who wrote it. Yeah. So I want to expand.
Potentially. I mean, I'd be happy to talk about that offline, but I really don't know what these subspace methods are.
Let's thank Nathan again, and then we'll move on to our last speaker for the session.